Okay, guys, today we're going to be looking at section 7.4. It's on the two special right triangles that we have in geometry that form the foundation for everything in pre-calculus, calculus, and beyond. So let's take a look at this right triangle here. It's a right triangle because you see it's got the right angle, but it's also an isosceles right. So I'm just going to label this as an isosceles right triangle. And I want to go through and figure out what some side lengths are. So I'm just going to call this side length something like 7. Well, because it's isosceles, the other leg also has to be 7. And then I'm going to call the hypotenuse C, because we always use C for the hypotenuse in right triangles. So I'm going to use the Pythagorean theorem and just write this out as C squared is equal to 7 squared plus 7 squared. That's what we would get. Now, normally, if we were just doing this for any regular right triangle, we'd go ahead and square the 7, get 49. We'd square the other leg and get whatever number that is, add them together, and then take the square root and simplify. But in this case, we've got exactly the same thing twice. We've got two 7 squares. So I'm going to write this as C squared is equal to 7 squared times 2. So I can't do that with other cases of the right triangle because I don't have the same number there. Let's see, it's 7 squared. Well, see, I'm actually wanting to solve for C, so I'm going to take the square root of both sides now. Well, the square root of C squared is just C. And now look at this. The square root of a perfect square is just the number itself. So this square root of 7 squared, I'm going to separate because it's multiplication or division only. There's no addition or subtraction. But this part right here, the square root of 7 squares, is 7 times the square root of 2. So I'm going to put that down over here, and this is 7 root 2. And we have all the side lengths for this particular right triangle. So I'm going to put these side lengths up here and just put them from smallest to largest. 7, 7, 7 root 2. Okay? Well, now I want to go through and use a different number. I'm just going to pick 23 for the leg lengths. And again, I want to solve for the hypotenuse. So I'm going to do the same thing again. C squared is equal to 23 squared plus 23 squared. But again, because it's isosceles, these two sides squared are exactly the same number. So I'm going to write this then as C squared is equal to 23 squared times 2. Now, the reason why I'm putting that perfect square up in front is because when I take the square root, that square root of a perfect square, that's what's coming out. So the 23 is going to come out, and so then I'll have the root 2 inside, and I don't have to skip. Again, take the square root, both sides. Well, this is just going to be C. Again, I can separate this as 23 squared times the square root of 2 because there's no addition or subtraction in here. And then this is 23 root 2, and that's the length of C. So I'm going to erase this now and put in this 23 root 2 for the hypotenuse. Putting it right here. And then I'm going to write down these side lengths again. 23, 23, 23 root 2. Well, there's a pattern here. And this pattern is what we want everyone to see. I'm just going to pick another one. If you notice right here, the legs, for both of these two, if you want the hypotenuse and you know what the leg is, all you've got to do is multiply by the square root of 2. So if I put down 5, 5, well, instead of going through the Pythagorean theorem again, it's just going to be 5 root 2. And this is another case of side lengths of this isosceles right triangle. Now, there's another notation for isosceles right if we look at the angles that are inside. So because these two sides are the same, that 90 degrees between them has to be split down the middle, and so they're both 45. And so often you will see this as a 45, 45, 90 triangle. Well, I'm going to put a few other examples down, but this time I'm going to start with the hypotenuse. I'm just going to say that the hypotenuse is 10 root 2. And I'm going to go ahead and put it over here now as the hypotenuse, the longest side. Well, if the hypotenuse is 10 times the square root of 2, how do you get the legs? Well, instead of multiplying by the square root of 2, we got to go the opposite direction, which is divide. And so both of these sides would be 10. So what is then the pattern for a 45-90 triangle, the ratio of the side lengths that occur? Let's call the legs both x, and this hypotenuse is x times the square root of 2. Now, if you know what the legs are, right? If you know those first, a side length is given. To get to the hypotenuse, you have to multiply by the square root of 2, right? So you're going from a leg to the hypotenuse. If you're going the opposite direction, from the hypotenuse to either of these two legs, you have to divide by the square root of 2. Well, let's take a case that's a little harder because the numbers that we've had so far have been very nice. But let's take something like this. Suppose we have, for our side lengths here, suppose we have the square root of 7. Well, again, we've got to multiply by the square root of 2. But what does that look like when you multiply it out? Well, again, it's the same root. This is a square root here. It's a square root here. And when no number is up there, it's always implied a 2. This is the square root of, see, now we can go through and multiply these radicands underneath. That's the square root of 14. So here's another right triangle, isosceles right. And again, the side lengths there are root 2 times bigger than the legs. Well, what about the hard case? The hard case is when you're given the hypotenuse and it's not something times the square root of 2. So I'm just going to pick 12. Let's go with 12 right here. And how do we go through and get the two leg lengths if you know that this hypotenuse is 12? Well, we've got to go the opposite direction. Instead of multiplying by the square root of 2, we're going to, again, divide by the square root of 2. And it's got to be for both sides. We're doing that for both because they're both the same. Well, I'm going to write here 12 divided by the square root of 2. We can't leave this number as the final answer because our final answers can never have radicals in the denominator, right? The only thing that we're allowed are for integer values when we're dividing. So how do I undo that square root of 2? Well, I've got to square it because it's a square root, which means you multiply that number by itself. So I'm going to do that in the denominator. if I do it in the denominator, I've also got to do it in the numerator. This number, root 2 divided by root 2, is equal to 1. So we're multiplying this 12 divided by root 2 just by 1. So the value stays the same, but the form is going to be just a little bit different. Well, in the numerator, multiplying across, we have 12 root 2 divided by, well, root 2 times root 2, again, that's root 4, the square root of 4, which is a perfect square. So the 4 comes out as a 2. Then we can go through and simplify the 12 with the 2. That's a 1. That's a 6. So this is equal to 6 root 2. Well, if this leg is 6 root 2, so is this one. And so I'm going to write these 6 root 2, 6 root 2, 12. And again, once you know what the lengths of the legs are, you just multiply by the square root of 2 and you'll have that hypotenuse, and that works. Well, there is an easy way to look at this other than going through all these steps down here, because this, it's true, it's correct, but it takes a long time to do every single time that you do the problem. Well, what's the fast way? Let me go through and erase this again. And I'm going to take a different number for the hypotenuse. We still have those same rules since we know the hypotenuse length. But let's take 20. All right? Here's what you do to make it fast. If you want to get the lengths of the legs, take half of 20. Divide 20 by 2. And then multiply by the square root of 2. Well, 20 divided by 2, that's just 10. And so this is 10 root 2. So is the other leg, 10 root 2. And again, here is a case, 10 root 2, 10 root 2, and then the hypotenuse of 20. The main thing to remember here for this entire section is the ratio of the sides, x to x to x times the square root of 2. Again, that's leg, leg, hypotenuse, because in this case, those two legs are exactly the same length. So that's the 45, 45, 90 triangle. Let's take a look at the second special triangle. This one is a 30, 60, 90. Now, other than the 90-degree angle being divided by 3, 30 and 60, there's nothing really special about this except for the fact that the length of the short leg is exactly half the hypotenuse. So for a 30, 60, 90 triangle, the key thing here is the short leg. Now it's got 2 legs, but the short leg's length is 1/2 the length of the hypotenuse. Now, that still leaves the other leg, the longer leg, which we've got to go through and figure out. So I'm going to plug in some values here. And I'm just going to start with 6 over here for the short leg. Well, again, that's half of the hypotenuse, so that's immediately 12. All right? Doubling and halving are pretty easy. So if you have the hypotenuse, you just take half of it. You get the short leg, you double it. Well, the 12 is the hypotenuse of a right triangle. Our Pythagorean theorem still holds true. C squared, whatever the hypotenuse length, is equal to the sum of the squares of the legs. So I'm going to plug these numbers in. 12 squared is equal to, I'll let this 6 be the a squared, plus b squared. So this side down here that we don't know, I'm calling that b. And we've got to go through and solve for b. Now, one word of caution. Do not write this as b squared is equal to 6 squared plus 12 squared just because the b is the unknown side. It is not the hypotenuse. So I'm going to go through and square these numbers out. 144 is equal to 36 plus b squared. Well, I've got to subtract 36 from both sides, and when I do, I get 108 is equal to b squared. And now then I need to take the square root of both sides. So I'm going to take the square root here, and I'm going to take the square root here. Now, what we've got to do to write this in simplest radical form is to find any perfect squares of that 108. Well, the 108 has a factor of 9 because the sum of the digits 1, 0, and 8 is 9, right? So 9 goes into it. 9 is a perfect square. Well, 9 times what? Well, again, this is from our multiplication tables. 9 times 12, all right? But 9 is not the biggest perfect square that actually goes into 108. In fact, if you look at the factors of 12, one of them is a perfect square. Well, again, which pair of factors? We got 12 and 1, 2 and 6, 4 and 3, and the 4 is the one that we want. Well, now then, let's take the 9, that's a perfect square, times the square root of 4, which is also a perfect square, times the square root of 3. This is 3 times 2 times the square root of 3, or when we multiply the numbers that are outside, 6 root 3, and that's equal to that longer leg length. Let me scroll this back up here, and I'm just going to put that in. This is 6 root 3. Now let's take a look at the values that we have for this one. It's going to be a 6 root 3, 12. Now, instead of going through several examples like we did for the 45, 45, 90, this also has its own pattern. And the pattern is this. You take the short leg, whatever it is, you multiply it by the square root of 3 to get the longer leg. You multiply the short leg by 2 to get the hypotenuse.